The end is in sight. We're getting close to our final exam. Our last topic is going to cover a little bit of physics. We're going to talk about forces and friction, and we're going to talk about work and energy a bit. All right, so when I talk about force, before I even go into the slides, I'm talking about, I guess, essentially a push or a pull. And there's some ways that seem very easy to us. If we have, our block is apparently on a hill, which is a whole other situation. We can tie a rope around our block and pull it and apply a force that way. That's an applied force. Or we can get behind the block and push it. Another type of force. But there are other forces we can consider that, aren't as obvious, like the force of gravity and the normal force. So we're going to get lightly into those. We've talked about force in other equations. When we are doing torque calculations, that twisting force is when we apply force at a distance away from a pivot point. We've also used force in hydraulics when we can apply a pressure to an area and create an output force at the front or rear brakes, or the input force from our brake pedal. So if we want to talk about forces, we're going to have to talk a little bit about Newton's laws. Newton's first law is that an object at rest will stay at rest. So if something's sitting there not moving, it's not going to start moving for no reason. And an object in motion will stay in motion. If something is moving, it's not going to stop moving. Does Newton's first law make sense to us intuitively? When I think about an object at rest, when I think about a ball on a table, yeah, it's going to stay at rest of its own accord. It's not going to suddenly get not sentient. It's going to be like, all right, time to get up and go and move unless something happens to it. However, when I think about an object in motion, say if I roll a ball or if I throw a frisbee, it doesn't just keep going forever. Right? Like it'll slow down and stop or fall. Something will happen to it to stop its motion eventually, as we observe here on Earth. So what's happening? There has to be forces that are working on those objects. I'll just summarize it up here. There we go. In the slides. We'll take this over to a vehicle application. What forces do we have when we drive? Well, if you're driving a car, and there's a headwind, that slows you down. That's a vector acting against you. What else could slow you down? Rolling resistance or friction of your tires if you're sliding. And by stepping on the brakes, we apply a force to slow ourselves down. Likewise, if we want to speed up, some of it is in our control and some isn't. If there's a tailwind, we're going to be driving faster than we think, or it's easier to drive. The force that we give to the wheels from the engine, the twisting torque, that accelerates us, that speeds us up. And friction actually acts both ways here. When it acts as a grip between the tires and road, that adds to our speed. So it can be both a rolling resistance or, a full-on static friction, or it can be a grip adding to our speed. So I'm going to continue to be a little boring and not get into the math yet, just because I want to kind of lay down the groundwork here, and we're definitely going to be looking at friction. So when I talk about friction, friction is a force. I often do my big F for force and then put a little f subscript for friction, the force of friction. And it's the force that resists motion. So it's the stuff that slows you down. So if you have two things in contact, and it doesn't matter if it's a box on an ice rink or if it's a wheel on a road, or if it's the wind on your windshield, those are all two surfaces that are in contact. That is creating friction. Now, how do we figure out how much friction we're going to get in a situation? Depends on what's in contact. Is it concrete with sandpaper? Is it ice with an ice skate? The mass of what's moving, and also the acceleration of what's moving. But we'll get into that in a second. First, I want to visit Newton's second law. And it's an equation. Force is equal to mass times acceleration. This is our big formula. Once again, it could make a triangle if you really want it to. You might be sick of the triangles by now. Could set up just like that little pyramid. Let's talk about the units though, because that is huge. We're going to work in metric, because metric we have a unit of force called newtons, and it's a made-up unit. It represents kilograms per meter, kilograms times meters per second squared. Where does that come from? This is a mass. This is an acceleration. So force equals mass times acceleration. When you go into this formula, you want to make sure you're working in kilograms, not grams. And acceleration is what we've been using for metric all along, meters per second squared. So remembering to recognize the difference between a speed and an acceleration from the units. Now, we're not going to work in imperial or US customary because our force will be in pounds and our acceleration will be in feet per second squared, which is fine. We've worked with those two. But then we're going to have to bring in a new mass. Slugs. Which is pounds per second squared per feet. Weight divided by gravity to take the gravity out of it. So we're not going to do that. It's too much. So we're going to stick with metric. Our unit for force will be newtons, which we will give the symbol capital N. And now we get to do some math, now that we know that formula. So let's look at number one, very straightforward. Checking my units, kilograms and meters per second squared, we're all good. So we know that we have a mass of 2,300 kilograms and an acceleration of 3.5 meters per second squared. And I want to find the force applied. So that is, let's just say, the force coming from the engine, delivered by the engine. So here we go. We're going to do 2,300 multiplied by 3.5. And we are going to get 8,050. And remember, our unit of force will be newtons. The next two questions just kind of spin this formula around. We have an acceleration in number two, 2.7 meters per second squared. We got a force already, 7,000 newtons. And we want to solve for a mass. If we rearrange the formula or use a triangle, we know that mass is equal to force divided by acceleration, which is going to be 7,000 newtons divided by 2.7 meters per second squared. And we're going to get that mass of about 2,593 kilograms. So keeping the right units. And number three, guess what? We've got a mass 5,400 kilograms. We have a force 3,375 newtons, and we want to solve for an acceleration. Acceleration is equal to force divided by mass. Don't do big divided by small. Respect where things go. The smaller number in this case is the force. We're going to divide it by 5,400 kilograms, and we get a smaller acceleration, 0.625 meters per second squared. Now, what am I assuming? I just have one force in this situation. That's not true. There's going to be friction forces, there can be other forces, could be forces that are generated by angles, whatever. We are ignoring that, and we're just using the basic formula for now. And that time has passed. That was brief. F equals ma is now getting some upgrades. We're going to bring friction back into the situation. So, like I said, what are we assuming? There's nothing working against that motion of that vehicle. We're not thinking about the rolling resistance between the road and your tires, the friction, the wind. We are not going to look so much at wind resistance, it's more complicated, but we will use a formula to find the force of friction or rolling resistance. And that formula will be right here in yellow. So remember I said when we talk about force of friction, we're going to have our big force symbol, but we're going to clarify that it's a friction force by giving it a little f. This funny u is called mu, and it's a value that you might have to solve for, but you'll usually be given. It's a coefficient of friction, and it depends on what materials are in contact with each other. It depends on a lot of things, temperature, whatever, but it will probably be given to us. And then we have this kind of mg portion of the formula. M is the mass of your object in kilograms. And g is the acceleration due to gravity, and that's a constant. So you're always going to use the number 9.8, or if you're pickier, 9.81 meters per second squared for the value of g. I'm going to bring back some math. Here's a nice website if you ever want to figure out coefficient of friction between your tire and various road surfaces, wet, dry, whatever. It's kind of handy. All right, so we have a situation here where we have a tractor that is either driving or sliding on ice. So we know that the formula for the force of friction is equal to mu times mg. Okay, here's our mass. We know that g is equal to 9.8 meters per second squared, and we just have to pick the correct value for the coefficient of friction. Now, if it is sliding, we're going to use the coefficient of sliding friction, not the other numbers. So we're going to use 0.6 from you. Here we go. What is the force of friction acting against the motion of this tractor? 0.6, 10,000 for the mass, 9.8 for the acceleration due to gravity, and we're going to get 58,800 newtons. That's a big force acting against it. So we'll see what's going to happen in a little bit. Okay, we're going to take a second situation where we're driving on ice. And if you think about pushing a tire versus rolling a tire, I'm not surprised that the coefficient of rolling resistance is lower. It's easier, right? It's easier to do that when you think about yourself physically doing. So this time from you, I'm going to use 0.2. Everything else will still the same. It's still a 10,000, I probably said pound, I meant kilogram, tractor. And the force of the acceleration due to gravity remains 9.8. And in this case, we're looking at 19,600 newtons for the force of friction. Now let's take it to number 3. If a force of 70,000 newtons was applied to the tractor, so this is like the push given by the engine, whatever have you, or you're dragging it, something is happening. There's a force applied to this tractor. And let's say we have, oh, it's drawing time. Yes, Guy, here is our tractor. And however it's happening, we are pushing it with 70,000 newtons in any case. And in situation 1, how much friction is acting against it? So notice the direction of the arrow is opposite our applied force. We get 58,800 newtons working against us. So what's a net force in situation 1? 7,000 newtons applied minus 58,800 newtons of friction gives us 11,200 newtons as a net force. Okay, and then we can use that to go back to our mass times acceleration and think about how fast this tractor is accelerating or not accelerating. In our second situation, we had the same applied force, but this time much less friction. So our applied force minus the friction force working against it is going to give us our net force of 50,400 newtons. So there's a new term, net force, after the mathing. And we're going to keep going with this. So we've got our sliding tractor, and remember we said the net force was, where was it? 11,200 newtons. Both of these tractors still weigh 10,000 kilograms, which making some notes from the previous slide. And while we're here, the driving tractor, the net force. So notice I'm putting a little N for net force now, just to keep it clear that I've already applied a force and subtracted the friction force working against it, because this is really what you've got now, what you're left with. Oh, sorry, that should be 50, sorry, I'm just going to go lazy. 50,400 newtons. Okay, so back to the second law. We have an equation. Force is equal to mass times acceleration. So if we're looking for the acceleration of an object, after we've resolved all the forces acting on it here, we can come in with this formula. So if we're looking for the acceleration, force divided by mass equals 11,200 newtons divided by 10,000. And we're going to get 1.12 meters per second square. Okay. Situation 2. What's the acceleration going to be? It's driving, not sliding. It has a much greater net force working in the way we want it, so I'm expecting a much bigger acceleration. Take the net force, I divide it by the mass of the tractor, and I'm going to get 5.04 meters per second squared, which is some serious stink from that tractor, possibly not realistic. Here's something much, much more evil than I would ever do to you, but you know, it's me trying to tie this forces and frictions back to our motion unit, bring it all together. Let's see if it works for me. I might be making some assumptions. What do we have? We have a mass of a vehicle. Interestingly, we have an initial speed, which is old school. We'll just write that down and ignore it for now. And then we have a couple of mu values, so mu1, mu2. All right, so let's see what they want to know. They want to know what the rolling resistance of the vehicle is. So they're looking for the force of friction when the vehicle is driving. So we're going to go and use at 0.01 for mu. We take the mass of the vehicle and we multiply by the value, constant g, acceleration due to gravity. And that should give us about 548.8 newtons. Question 2. I'm going to make my pen a little thinner so we can fit it in there. If the engine supplies 1,500 newtons to the wheels, what is the total force on the vehicle? So you're getting a push, let's say, of 1,500 newtons. But you have 548 newtons of friction acting against you. And what is our net force? So our total force here is the net force is what they're looking for, net. And that should be 951.2 newtons. Now that we have a net force, we can think about the acceleration. We know from our equation that acceleration is going to be the force, the net force, divided by the mass. So we have our 951.2. And if we divide it by the mass of the vehicle, which is 5,600 kilograms, we are going to get an acceleration of 0.17 meters per second. So as that vehicle is driving on that wet asphalt road with a force supplied for the engine, we are accelerating at this speed. So now let's change the scenario. The vehicle is going to somehow start to slide. The transmission is knocked into neutral. I don't know what you're doing with your brakes. Doesn't look like much is happening. But we're just using friction to stop this vehicle. So we're back to the friction formula. But this time, because we're sliding, we have to use our little 0.55 for mu for that coefficient of friction, because that's a sliding one. All right, our mass was 5,600 kilograms, and G is still 9.8. And this time, the force of friction is much bigger. It's 30,000 and change newtons. Okay. So they want to know now in number 5, what is the deceleration? So the slowing of the vehicle. So this is just, we were going along at 50 kilometers an hour. Our transmission, we started sliding. We kicked the transmission to neutral, so we're providing nothing else. We're not braking for some reason. So we're just taking a deceleration using this force of friction. Now, you could say deceleration is negative. Well, the force of friction could be considered to be negative too, right? Because if you have no applied force, 0 minus 30,184 is negative. So you can do it that way, or you can just be like, if it's a deceleration, maybe I'll make it negative to make things work later on, or maybe I don't have to worry about that. Whatever floats your boat. Okay, so let's think about this. We know that acceleration, deceleration is equal to the change in speed over the elapsed time. I got ahead of myself there. That's not what I wanted to say. We're not dealing with time yet. We're just dealing with force. So we know that force is equal to mass times acceleration. We need to find the deceleration. So we're going to take the force and divide it by the mass of the vehicle. I got too excited, wanted to do motion stuff. I take my friction force, the only force I've decided is action. I'm dividing it by the mass of the vehicle, and I'm going to get 5.39 meters per second squared. Okay, and you can make that negative too if you want, because you know it's a deceleration. How long is it going to take this vehicle to come to a stop? So now we're bringing in time. We're solving for time, and this equation, force equals mass times acceleration, is not going to do it for us. So I'm going to look around and see what I have. I have an acceleration or deceleration. I have an initial speed, right? Let's say we kick that vehicle into neutral. We're going at 50 kilometers an hour. I have a final speed because it's coming to a stop. So it's 0. So my final speed is 0, and because I'm dealing with the change in speed, acceleration, time formula, I'm going to write meters per second. And my initial speed is 50 kilometers an hour, and I'm going to go over here and divide that by 3.6 to change it to meters per second, because when you work with the acceleration formula, you want your speeds in meters per second. So I'm going to get 13.9 meters per second. And I'll add in that deceleration, negative 5.39. What's my change in speed? Change in speed is the final minus the initial speed, is 0 minus 13.9. And here we see that negative coming through to keep things consistent. Negative 13.9 meters per second. So you got slower, of course. Now we're ready to go back to solve for time. Time is equal to the change in speed divided by the acceleration. In this case, that's going to be negative 13.9 meters per second divided by negative 5.39 meters per second squared. And when you do that, the only unit that's left is time, so it's 2.58 seconds. So the vehicle will take 2.58 seconds to come to a stop. That was epic. Let's get away from the math, go back to Newton's law, and we're going to talk about Newton's third law, which is for every action there is an equal and opposite reaction. I find this one a little more hard to conceptualize. So when we were working with the friction force, we had our mu, but we were multiplying it by mg. It just kind of came out of nowhere. But what that is, that's a force of gravity acting on any object. You know, if you have a mass, gravity is pulling down on it at 9.8 meters per second squared. It acts on everything. So this is what makes things fall, mg. But it's also there if you're sitting. Gravity acts on you when you're falling through the air, but it's also acting on you when you're standing on the ground, but you don't suddenly start sinking into the ground if it's not a sinkhole or a quicksand. You're not going to just burrow through down to the ground. And why is that? It's because to balance the force of gravity when you're sitting on the ground, there is what we call a normal force. Okay, and it is the ground acting up on my feet. So in this picture here, we have, you know, the weight or the pulling down mg of that metal block. But what's also happening is there's a normal force, which is pushing up, the table pushing up against the thing to keep the block, to keep the forces in balance. What does that mean for us? If you want to lift something up, you need to overcome the force of gravity. So how much force must I apply to lift a 250 kilogram engine? Well, what is the force of gravity on that engine? Force of gravity, another subscript, is equal to mg, so mass times the acceleration due to gravity. So we're going to have that 250 multiplied by 9.8, which will give me 2,450 newtons. So if I want to lift that engine off the ground and I apply 2,400 newtons, it's not going to lift. But if I apply 2,500 newtons, I will lift it very, very slowly. And it can be a confusing, but you can see this happening around, like if you were swimming in a swimming pool and you pull with your arms to push against the water to propel yourself forward. The water is pushing back against you and moving you. There's lift that is kind of using this law. If you, and another one, if you launch a rocket, so if you push down against the bottom of the rocket, the gases are going to push up on you as well and move you forward. One last discussion slide, and then we'll finish with math. So let's consider a car accident, hopefully a very minor one, where you just kind of drive off the road, and as you're driving off the road, you are braking, and you just nudge a tree gently. Okay, so how are the laws in play here? So the first law, when you touch that tree, you're going to jerk forward, right? Your body wants to fly forward. Your body wants to stay in motion. Let's think about Newton's second law, force equals mass times acceleration. As you apply the force onto the brakes, you are causing a deceleration to happen in the car. And Newton's third law is where your seatbelt comes in. You're trying to fly forward, your seatbelt is trying to keep you in the car. It's working opposite your force forward. That's a lot of stuff to digest, so just let's sum up with typical questions you might see on our assessments. So question 1, we've got a coefficient of friction, mu, we have a mass, and we want to know the force in friction. We remember that the force of friction is mu mg, mu times that normal force, or the weight of the object. Thinking about different things now. Okay, we're going to go 0.35 multiplied by 5 multiplied by 9.8. Force of friction acting between those two objects is 17.19 newtons. Another typical question, number 2, what's the acceleration? Well, we have a mass and we have a force, so we can find that, and there's no other information given, friction or anything, so we ignore that, and we just use this very basic formula. Acceleration is 20 divided by 5, which will give you 4. Remember the units, meters per second squared. Number 3 is like a little more challenging, but not terrible. We have a mass and we have an acceleration, so we can find a force there, and I see there's friction forces too, but if I'm solving, with this formula, I'm finding the net force, right? This has already happened. This is going on right now, so we're going to take 10 kilograms and multiply it by 2.5 meters per second squared, and we see that the net force in that situation is 25 newtons. So that's not what we applied, because if we only applied 25 newtons and the friction forces were 50 newtons, we're not moving, right? We didn't overcome the frictional forces. So we need to remember that the net force is whatever we applied to it, however we pushed it or pulled it, subtracting the force of friction that was working against us. So we know that we had 25 newtons as a net force, because that's what we saw, that it was accelerating. The acceleration of that wagon told her, is it a wagon? Yeah, told us that. We don't know the applied force, but we know that 50 newtons were working against us. A little bit of math, if you want to have 25 left, what subtract 50 equals 25? X equals 75 newtons. And then bringing into our force of gravity, what force does a 65 kilogram transmission lying on the shop floor exert on the floor? Let's see the light. Here we go. So we are just going to use a straight up formula. That's a mass. What's the other thing we need? An acceleration, but here's 9.8 meters per second squared. So we're going to go F equals mg. So that's a force, that third law. 65 times 9.8, 637 newtons. So the fact that it's not going anywhere, the ground is exerting 637 newtons back onto the transmission. And number 5, super easy. We're going to apply a force of 200 newtons to push something. There's a very tiny amount of friction force, which is 30 newtons, and what's the total force on the transmission. So we're asking for the net force, and that's all we're asking for here. So this is a nice question. 200 minus 30 equals 170 newtons. So there we go, a very light dusting of forces and frictions, mostly because I've forgotten more than I ever learned about it, but hopefully this will get you through this last unit that we're covering in 8521.